All right, everybody, this is the lecture on magnetism, part one of the lecture on magnetism. Hope you had a good Easter. So let's start with a definition of what magnetism is. The word magnetism comes from the word magnetite, which was the first naturally occurring magnets that were discovered. And they're named after the Greek area called Magnesia, where they were first discovered. These were iron ore rocks that were mined out of the ground and were discovered to have magnetic properties. They attracted certain metals. So metals that are attracted to magnets or can become magnetic are called ferromagnetic. The word ferro means iron, and so the earliest known magnetic materials were iron, and so that's why we call them ferromagnetic. But we now know that other metals other than iron can also display these magnetic properties. Cobalt, nickel, and a lot of other alloys of different metals can be used to make magnets. Now, one of the most noticeable things about a magnet is that it has magnetic poles. Those are the ends of a magnet where its magnetic force is concentrated, and we name them based on the fact that the north pole points north. So if you take a magnet and freely suspend it, which is all a compass really is, the compass needle is a magnetized piece of metal, it will align itself with the Earth's magnetic field. Now, in the second video, we're going to talk about the Earth's magnetic field. So one pole will align itself northward. We call that the north-seeking pole, or for short, we just call it the North Pole magnet. That's the point that will point toward geographic north. And then the other pole, the other end, will point south. We call that the south-seeking pole. Now, there are some very important similarities between magnetic poles and electric charges. Like electric charges, opposite poles attract each other, and like poles repel. Those of you that are taking a lab did a lab a few weeks ago where you pushed two magnets together with their opposite poles, and you saw that they repelled. Turn one around. Their like poles would repel. Turn it around so that you have the opposite poles and they would attract. So they're similar in that way with electric charges, that you have two types of charges, positives and negatives. Like charges repel, opposite charges attract. You have two types of magnetic poles, north and south. Opposites attract, like poles repel. There is one important difference though. And that is that electric charges can be separated. You can have positive charge over here on one object and negative charge over here on another object. Magnetic poles, north and south, cannot be separated. If I were to take this magnet and cut it in half and try to separate the south pole from the north pole, I would not end up with a piece that was just a south and another piece that was just a north. I would end up with two smaller magnets, each with a north and south pole. If I tried to cut it in half again, I'd end up with still smaller magnets, each with a north and south pole. So as of yet, we have not discovered a way to produce a monopole, which is a single isolated magnetic pole. There are some scientists who think that this is maybe possible, but so far we haven't been able to pull it off. As of yet, magnetic monopole does not exist. Another similarity between electric charges and magnetic poles is that there is a magnetic field. We discussed how a force field is the region around an object where you can experience its force. In this case, we're talking about the magnetic force. With electric charges, we call that the electric field. With a magnet, we call it the magnetic field. Now, with electric charges, that electric field was mapped out by tracing the path that a small positive test charge would move if we placed it close to that electric charge. For a magnet, we map out the magnetic field by tracing the direction that a small test magnet, it's not positive, it's not a charge, it's a magnet, a small test magnet will point. So you see if I move this compass, which I'm using as a test magnet, around this larger magnet, that the needle changes the direction that it is pointing. And that allows us to map out the magnetic field. Now the field is kind of complicated around this horseshoe-shaped magnet. on your PowerPoint, you have a simplified magnetic field around a bar magnet, so it's a little easier to see the properties of the magnetic field. Now, one key difference between the magnetic field and the electric field, one is they're produced from different things. One is produced from an electric charge, the other from magnetic properties. But the electric field lines, if you remember, began on positive charges and radiated outward, and then ended on negative charges where they radiated inward. So they had a beginning and an end. Magnetic field lines always form closed loops. They do not have a beginning and an end. They radiate out from the North Pole around the magnet and back into the South Pole, but then they also run through the magnet, forming a closed loop. They do not have a beginning and end. So that's a key difference between the magnetic field and the electric field. All right, next thing we want to look at is what causes magnetism. So here I've got three objects. I've got a permanent magnet, I've got a paper clip, which is attracted to it, and I've got a plastic marker, which isn't affected at all. What is it about these three materials, one that's a permanent magnet, one that can be magnetized, and in fact, if I take another paper clip, it can be attracted to the first one, so it can display some magnetic properties. It's kind of weak, but there you can see it's being attracted to it just a little bit. So this can become a temporary magnet, and then we have this object, this material, which isn't magnetized at all. Initially, people thought, since there were these similarities between magnetic poles and electric charges, two types, positive and negative, north and south, opposites attracting, like poles repelling. People originally thought that magneticness was due to the buildup of something, like electric charge is due to the buildup of electrons. An object is negative because it has more electrons than protons. An object is positive because it has fewer electrons than protons. So people originally thought that the North Pole had more of something that the South Pole was deficient in, that there was some type of magnetic particle, like a magnetic analog to the electron. Turns out that's not true. And a guy named Hans Christian Ørsted determined that magnetic properties are not due to the buildup of something the way electrostatic charge is, but instead are due to moving electric charge. So there are moving electric charges in this magnet that give it its magnetic properties. Now you might be wondering, how is electric charge move into this? We've already talked about current electricity and how you have to have a source of electric potential, like a battery or a generator. There's no battery hooked up to this thing. There's no current flowing through it, and that's true. But there is moving electric charge. If we look at the individual atoms that make this magnet up, they are made up with a nucleus that has the protons and the neutrons, and around that we have the electrons, which are in orbit around the nucleus. So they are moving. So these electrons orbit the nucleus. That's moving charge. Not only do they orbit the nucleus, they also spin on their axis, so they move in that way. So on a supermicroscopic scale, there is moving electric charge. And each little atom acts like a tiny magnet. There is a magnetic field generated by the moving electrons in each atom. Now, that doesn't explain why this is different from this, because this has moving electrons too. There are electrons in orbit around its atoms, yet it does not display any magnetic properties whatsoever. Well, the reason has to do with an idea that Ørsted came up with called magnetic domains. All right? A magnetic domain is a tiny region in a material where all of the atoms, where their motions, the motions of their electrons, their spins, and their orbit around the nucleus, result in an overall magnetic field. So it's a small, tiny group of atoms that are all oriented in the same direction. So all of their electrons are kind of moving together. All right? Now, all materials have these magnetic domains. The plastic pen, and the permanent magnet, and the paperclip. The difference between the permanent magnet and the pen is the arrangement of these magnetic domains in an unmagnetized material, like the pen. The magnetic domains are completely random. All right, the orientation is random. So some will be pointing up, some will be pointing down, some will be pointing to the left, some will be pointing to the right. So there are magnetic fields in this material. But because of the fact that they're all jumbled up, they end up canceling each other out. For every magnetic field that is pointing up, there's another magnetic field that's pointing down, and they cancel each other out. For every magnetic field that's pointing to the right, there's another one pointing to the left, and they cancel each other out. And the end result is there is no overall magnetic field for this pin. In the permanent magnet, in a magnetized material, at least a majority of these magnetic domains are oriented in a common direction, giving that overall magnetic field. The more of these magnetic domains that are arranged in the same direction, the stronger the magnetic field. So this magnet, it's big and heavy, but it's actually fairly weak. We've got some pretty strong magnets in the demo room that I'm going to bring for some demos next week. But the stronger the magnet, the more of these magnetic domains are arranged in a common direction. So that's what makes this a magnet. It is the orientation of the magnetic domains. Now, what about this material, this object, which kind of falls somewhere between? I mean, it by itself is not magnetized. All right, this isn't attracting the other paper clip, but it is attracted to this magnet. All right, and when it is in contact with this magnet, it can become magnetized. So this is a temporary magnet as long as it is in contact with this fairly strong permanent magnet. Well, the magnetic domains in a paper clip like this, in a temporary magnet, are generally unorganized. So right now the magnetic domains are in random directions. It by itself is not demonstrating any magnetic properties whatsoever. But if it comes in contact with a permanent magnet, these magnetic domains are flexible and can temporarily align themselves. That gives it magnetic properties and allows it to be attracted to the permanent magnet while it is close to or in contact with the permanent magnet. All right. Now, if I remove it, the magnetic domains go back to being jumbled up and it loses its magnetic properties. So it's only a temporary effect while it's close to the permanent magnet. The permanent magnet, the magnetic domains are fixed in their aligned positions. As long as I don't do anything drastic to this, the magnetic domains are going to stay aligned and it's going to keep its magnetic properties. Some of the drastic things I could do to this to unmagnetize it would be to heat it up. If I got it close to its melting point, then the heat would cause the magnetic domains to shift and get jumbled up and it would lose its overall magnetic field. Or if I took a hammer and just beat it, striking it a whole bunch of times would cause those magnetic domains to get jarred out of place and it would lose its magnetic properties. All right. So that's an overview of magnetism. In part 2, we're going to talk about the Earth's magnetic field.